Okay, reviewing what we did in class today. We started with two functions, x1 of t, x2 of t, which could easily represent two balls running down parallel ramps, or maybe even two balls of different diameters, the first of greater diameter than the second, running down the same grooved track. Now, you should understand the nature of these functions. You should understand that this function is a shift of 10 seconds to the right from the quadratic function you get if you didn't have the negative 10 seconds in there. That's kind of an important understanding, and I'm not going to go over that. That's pre-calculus, graphing functions by transformations. It works out very well with quadratic functions. If you've lost track of how to do that, you really need to review that. It's just part of the mathematical toolkit that you need. In any case, we have these two functions, and we asked a couple of questions. When are the objects at the same position? When and where do the speeds match? Now, what's our strategy? Of course, I asked the class for this and got a pretty quick response. Graph the functions and visualize. Very good thing. Now, if you graph the functions using your graphing calculator, that's still a good thing, but you really should use graphing skills that you've built in your pre-calculus and calculus classes. Especially these are just quadratic functions. They're not difficult to graph. Now, the numbers get a little messy, but you should be able to construct an approximate graph using those techniques. And you're going to get a graph that looks like this. The vertex of this graph will be to the left of the vertex of this one, this being the x1 function, this being the x2 function. And the x2 function has the greater coefficient of t squared. That's going to be 0.3 meters per second squared. And that's going to make this graph narrower than this graph. Now, these are both parts of parabolas. This is part of another parabola. This parabola is narrower than this one for reasons that you should understand. Again, if you don't, you really should go back to a pre-calculus book and see that you do. In any case, you can see from the way these graphs match up that there's a point at which they intersect, and that'll give you the time at which the speeds or the positions are the same. And of course, knowing the times, you could plug that value of t in for either of these and you would get the position, so you would get the point on the graph. Okay, that's a good aid to visualization, but of course we want an analytic solution, and that's obtained pretty easily by setting x1 of t equal to x2 of t. When the position of this object, which is x1 of t, is equal to the position of the second object, which is x2 of t, then the objects are at the same location. And setting this equal to this expression is quadratic in t, this expression is quadratic in t, so the equation will be quadratic in t, so you know you can solve this for t. I'll comment that if it was an impossible situation, which it would be if this was 0.2 and this was 0.3, then this one would be to the left. The vertex of this graph would be to the left of the vertex of this graph being basically steeper. This object would never catch up with this object if you switched these accelerations. Solving the quadratic, what would happen? You should think about that for a second, but I'm going to tell you. You're going to get a negative under the radical. You're going to have a negative discriminant, and you're going to get no solution. So be aware that things like that happen. No solution to the quadratic function that answers a question means that the question has no answer, at least not in real time. Okay, then the question of when and where do the speeds match. When the speeds match is easy. That occurs when the velocity of the first equals the velocity of the second, and those velocities are the derivatives of the position functions. So we very easily get this function, these functions. A derivative of a quadratic function is a linear function, so this is a linear equation, very easily solved. Now, how do we visualize that? Well, the velocity on an x versus t graph is the slope of the graph. So we're looking for a point on the t-axis where if we move up to this graph and then up to this graph, the two slopes are identical, meaning that the graphs are essentially parallel for that value of t. Now that's going to occur somewhere around here. I don't know that I drew that particularly well. But you see that can happen. And you see that at other points out here, this graph is steeper than this one. Now let's use a t out here. This graph is steeper than this. If we use a t over here, this graph is much less steep than this one. Now the point of starting with this situation is that we have situations in your problem set for today where you were asked to, or either that and or in the labs, where you were asked to answer questions that are going to end up being set up with functions that look a lot like this. So we're going to move on to that idea.